to join, and then we can start. And then for students, Professor K really want to see your reaction to the seminar. So if you can keep your camera open, it will be wonderful. So he can see whether you understand the thing he will teach today. And then for students, Professor K really wants to see your reaction to the seminar. Okay, I think I'll start recording and then we can start. Okay, I think I'll start recording. Good afternoon, good evening, and good morning for students from different time zones. Welcome to the Youth Educational Forum. This is the fourth seminar of 2022. We started this forum since 2018. And today we are very glad that we invited Professor Ni and Professor K to give us the wonderful seminar. So first, I would like to introduce Professor Ni, and then he can introduce Professor K. So Professor Ni is a professor of mathematics at Caltech. His research interest is low-dimensional topology. Before coming to Caltech, he went to college and grad school at Peking University and then Princeton University, and did his postdoctoral work at the Columbia University and MIT. And he has a various number of awards and fellowship through his career. So now I would like Professor Ni introduce Professor K.
Well, okay, thank you very much. So it's my pleasure to introduce Professor Matthias Kreck. Professor Kreck is a world-famous topologist. He got his PhD in 1972 at the University of Bonn. And he was the director of the Oberwolfach Mathematics Research Institute. And he was also the director of the Hausdorff Institute at Bonn. So now he is a professor emeritus at Bonn. So Professor Kreck is also a cellist. When I was a postdoc at Columbia University, Professor Kreck was also a visitor there. So every weekend he would go to the Central Park to play the cello. Of course, not for money, just for fun. So today he will talk about the Two Square Theorem. So Professor Kreck.
Yeah, it's a great pleasure to be with you, and I'm very impressed that so many young people take part on a Saturday. When I was young, there was still the Saturday a school day in Germany, but now this is long over, and I don't think any pupil in Germany does any mathematics on Saturday. So I'm very impressed that you do that. As you can hear, I'm not a native speaker, so my English is not very good. And if you don't understand my English, just interrupt. And if you don't understand the mathematics, also interrupt. So I would like to present to you today a result which has the flavor of serious mathematical research as we do it today. It's an old result, but still people are thinking about this result. So you will see an example of how mathematics takes place nowadays in the universities. The professors of mathematics do such a research. It's, of course, a well-chosen example since it uses only mathematical objects which everybody knows. Even my small grandchildren know what, and the result concerns natural numbers. And there is a cultural difference. In Germany, 0 is a natural number, but in other countries, 0 is not. So the natural numbers are just the numbers 1, 2, 3, 4, 5, and so on. These are the natural numbers. And although they are so easy to define, everybody in the world, in which country, at least after, say, 2 or 3 years in school, knows the natural numbers. So this is so basic, and one could think that in mathematics everything is known about natural numbers. But the contrary is the case. Natural numbers are very mysterious. Natural number are very mysterious. So easy and so complicated. And a lot of modern research takes place in number theory, not my area. Modern research in number theory. So some of the very, very best mathematicians think about problems which are easy to formulate and extremely hard to answer. And you will perhaps see a little bit of this flavor of the natural numbers. So easy problems and so hard to solve. There are many, many unsolved problems, fundamental problems in number theory. And the problem I'm discussing now is solved since several hundred years, but it's in the flavor of other problems which are not solved. So I want to introduce you to the problem. So that was just the introduction. And for the problem, we have to agree on what a prime number is. So I asked now the students, please raise, those who can see, raise your hand, who have heard what a prime number is. Prime number. Yeah, there are a few hands up. Not everybody, and I wanted to, almost everybody, many know what a prime number is. So if we would be in the same room, I would now ask one of you to go to the blackboard and write down the definition, but now it slows down too much. So the definition. Yeah, a natural number. And although the definition applies for the number 1, we don't do this. We exclude the number 1. And do you know this sign? Greater 1, greater than 1 is called a prime number. If it is only divisible by 1 and itself. It is only divisible by 1 and itself. And I suggest that together now you put on your microphones and you tell me the prime numbers you know. We start from the smallest and go up. So what is the smallest prime number you know?
2.
2. Very good. So examples. The next one.
3.
3. The next one.
5.
5.
5.
The next one.
7. 7.
Very good. The next one.
11.
11.
11.
Okay. The next one.
13.
13.
Very good. The next one.
17.
17. 17.
17. The next one.
19.
Wow, you are so good. The next one.
23.
23.
Ah, you seem to know all prime numbers. The next one.
29.
29. 29.
Very good. The next one.
31.
Okay. And I write and so on, which is of course a lie. Because of this is one of the biggest problems in mathematics, which nobody knows how this sequence goes on. Nobody has a formula for next prime number, next prime number, next prime number. But for small numbers up to 100, we would be able to write them all down. And the prime numbers are so important since every number is a product of prime numbers. Perhaps you have heard that already. So it's actually a theorem. Every natural number can be decomposed as a product of prime numbers. Prime numbers. So to know all numbers, it would be enough to know all prime numbers. And that's, nobody knows that. Very, very mysterious, difficult problem. And now we ask a question. So a prime number is not decomposable, can be not written as a product of two numbers, except the boring possibility. For example, 31 is 1 times 31, but nobody would write that. This is stupid. So it's not stupid, but it's not useful. So the question is, can one decompose the prime numbers in some other way? Can one decompose prime numbers in some way? And I would add to this, in some interesting way. So how do I erase? Here I can erase in some interesting way. And we could spend the whole hour speculating what interesting is. And I give you a suggestion, and you can say, no, this is not interesting, and then you can leave the seminar. But I hope you will say, no, let's wait. Perhaps this is interesting. The suggestion is, since we cannot write it as a product, we write it as a sum of products. But a sum of products would involve 4 digits, the first two, the second 2. And we want to involve only 2 digits, 2 numbers. And so the suggestion is the question. And that's the fundamental problem we want to discuss today. Given a prime number, and I use a letter. I call it P. It could be 31, it could be 29, it could be one of the numbers you have there. Stands for one of the prime numbers. The question is, are there two natural numbers, m and n, this could be 3 and 4, whatever, such that P is the sum of the squares. So it's m times m plus n times n. So P is the sum of two squares. Oops, squares. So we could discuss very long whether this is an intelligent question, but perhaps in the end you will say, yeah, this is a good question. At the moment it looks a little bit, perhaps a little bit arbitrary, but it is a good question. So to get familiar with this problem, we together go through the prime numbers you have given to me and we answer it together. So we make now a table. And we write down the different prime numbers and we try to decompose them. So the first prime number was 1. Is this, can you write this as a sum of some number times some number plus some other number times some other number? Yeah, please tell me the answer where the hands is up. Yeah, is there somebody who can tell me? 2 is equal to what? It's the sum of two squares. It's very simple. It's 1 times 1 plus 1 times 1. Do you agree? Do you agree?
Yeah.
Probably. Yes, hopefully. I like these answers. Okay. That's important. Do you agree? 2 is equal to 1 times 1 plus 1 times 1. That's stupid. It is true. So 3. Can you write 3 as the sum of two products of a number with itself? Probably not, I heard. Let's try it. So the first number would be 1. We could try to write 3 as 1 times 1. Yeah, plus 1 times 1, that would be already 2 that we have. And the next number is 2. And 1 times 1 plus 2 times 2 is too big. So, no. You all agree we cannot write 3 as the sum of two products of natural numbers. Agree? Please raise your hand if you agree that 3 cannot be written as the sum of two squares. Oh, many agree. I'm happy. So now we go to the next prime number. This is 5. Can you write 5 as the sum of two squares? Ah, I saw it already. Yes. And what is the number? What is the answer? How?
1.
Yes, please.
1 times 1 and plus 2 times 2.
Yes, very good. And I'm allowed to write 1 squared plus 2 squared. Do you know this notation? Yes, you know that.
Yes.
Okay, 5 is possible. 7. I see already no. Many people say not possible. It is not possible. Yeah. 1 times 1 plus 2 times 2, what we had already is 5. 1 plus 1 plus 3 times 3 is already too big. 2 times 2 is already 4. plus 2 times 2 would be 8, too big, so it's not possible. 11. What do you think?
Three squared plus
see.
1 squared, or 3 squared plus 1 squared, yeah.
But 3 squared plus 1 squared is what? 3 times 3 is 10, plus 1 would be 10. 3 times 3 is 9, plus 1 would be 10. So, not possible. It's not possible, and several have written that already. 13. I see already. 4 plus 9 is 2 times 2 plus 3 times 3. Let's do the next, 17. They are quick. 4 times 4 plus 1 squared. 19. There are already 23 doesn't work. I see already 19 doesn't work. So you can do that. So now I give you an example where you can work a little bit harder. It's a little bit longer number. So it's a long number. So P equal 2, 3, 0, 5, 8, 4, 3, 0, 0, 9, 2, 1, 3, 6, 9, 3, 9, 5, 1. So that's a prime number. We cannot see that easily, but you find it on the internet, and Professor Google never lies, so it is a prime number. And yeah, without a computer, even 10 hours might not be enough to decide that question. Yeah, by trying it out, you have no chance if you don't use a computer. With the computer, you can decide it quickly. A computer is so fast that it can try it out. But we don't want to use the computer, and we want to understand something. And now I want to tell you a first theorem. This is a more general theorem. Namely, so the prime numbers, except the first prime number 2, is always an odd number. Because of it, if it were an even number, it would be divisible by 2. So all prime numbers except 2 are odd numbers. So it's an important observation. Numbers are odd numbers. And the theorem concerns odd numbers. And the theorem is, if an odd number, not necessarily prime, is, let's call it k, is the sum of 2 squares, so P equal n squared plus m squared, then if you subtract 1 from P, then it is an even number and it's divisible by 2. But then it is not only divisible by 2, it is divisible by 4. So if you have an odd number, you subtract 1, then it is divisible by 4. Do you all understand the statement, what it means? Not the proof yet. So please, hands up, you understand what this theorem says. Yeah, you have an odd number, you subtract 1, and then it's divisible by 4. I see many people understand it. If not, ask me. That's just the statement. And now we do like professional mathematicians. We write proof and we prove it. Yeah. Okay. So we start with k is equal to n squared. And so we should be slow. Suppose k is n squared plus m squared. It's in particular the sum of two numbers, natural numbers. And if an odd number is the sum of two numbers, then there is something we can say about these two numbers. If an odd number is the sum of two numbers, then one of the numbers has to be even and the other has to be odd. Because if you add two even numbers, the result is clearly even. But you all know if you add two odd numbers, 3 plus 5, then it is even. So if k is odd, what we assumed, then either n squared is even. Oops, what's going on here? N squared is even, and then m squared is odd, or n squared is odd and m squared is even. Do you all agree? Hands up. If you have an odd number, it is the sum of two numbers, then one of them has to be odd and the other even. Agree, agree, agree. Oh, I see many agree. So now we make a little other observation. So by changing the order of the two numbers, if necessary, we assume, after perhaps changing the order of these two numbers, that now n squared is even and m squared is odd. And my question is, what does this imply for n? If n squared is even, what does this imply for n? If n squared is even, yeah, then it has also to be even. So this implies that n itself is even. Yeah, because of, if it were odd, the product of two odd numbers is always odd. And so it also implies and that m itself is odd. So the square is even if and only if the number itself is even. The square is odd if and only the number itself is odd. You agree? Hands up, please. Otherwise, I explain it again. Yeah, I see many agree. So now we know something about n. It is an even number. And to be an even number, n even, is equivalent, yeah, we can divide it by 2. So that means n is 2r for some number r. Agreed? Of course, even that means it. If n is odd,
还没有让我做题，他才让我听，他给我讲一个新的 theorem。 对，你就听听好玩就行，就听听有趣儿，它这真正的 math，而不只是 calculate。
I hear something
非常
which irritates me a little bit. I'm sure it was very important and correct, but we concentrate. So if m is odd, do you know how we can write an odd number? An odd number is the sum of an even number plus 1. Clearly, if you subtract 1 from an odd number, then you get an even number. And an even number was a number of this form 2 times something. So then m is of the form 2s plus 1 for some s. You agree? An even number is of the form 2r, and an odd number is of the form 2s plus 1. Already some people have already found the solution, but we do it slowly. Don't look at the solution others give, look at my solution. And although if we would be in the blackboard in the room, I would ask you to give the answer. So now we are ready to prove our theorem. Namely, we know, so now we come to the main step. And the main step is just computing. So we assume that k is equal to m squared plus n squared. And m, now we just do what we do in school. M is 2s plus 1. So it's 2s plus 1 squared plus 2r squared. You agree? I just have put for m 2s plus 1 and for n 2r. And now we just compute, and you use a formula which is called binomial formula. Who has heard about this binomial formula in school? A plus b squared is a squared plus 2ab plus b squared. Oh, many have heard that. So 2s plus 1 squared is 2s squared, which is 4s squared, plus 2 times 2s times 1, this is 4s, plus 1 squared is 1, plus 2r squared is 4r squared. And now we do something I like most in school. I put the 4 in front of the bracket, and it's 4 times s squared plus s plus r squared, and we should not forget plus 1. And now we are ready. So you agree with this simple computation? Hands up if you agree, you understood. I just make computations like you do in school, only with letters instead of numbers. Yeah, not so many agree. Should I do this again? No, more and more agree. Okay, so this implies k minus 1. We wanted to say something about k minus 1. Okay, we bring 1 on the other side. It's 4 times s squared plus s plus r squared. So 4 times something. So k minus 1 is divisible by 4. I hope you all agree. Any odd number, if it is the sum of 2 squares, if you subtract 1, it is divisible by 4. In particular, this holds for all prime numbers. So, in particular, for prime numbers p greater than 2. 2 is not true. 2 is not an odd number. We have if p is of the form m squared plus n squared, then p minus 1 is divisible by 4. And now we look back into the history, far, far back. I don't know when was America, when did Columbus go and find America? Which year or which century? I don't know, long ago. And we go back to the 17th century. In France, where they have the good wine and the good food, there was a lawyer and mathematician with name Pierre de Fermat. Who has heard this name Fermat? He's very famous for number theory. Okay, and he studied this problem. He studied, like we do it today. He found this problem very interesting. I don't know whether he was the first one. He studied this problem. And of course, he had no idea how one can decide when a prime number is the sum of two squares. He had no idea. But I'm sure, I haven't checked this, he knew our theorem. So I assume he knew our theorem. So he knew that all prime numbers bigger than 2, if they are the sum of two squares, if you subtract 1, it is divisible by 4. And he wondered, when is this possible? And I guess, I don't know that, he did what we did in the beginning. He tried it out. He tried it out and made large tables with prime numbers. And to each prime number, he wrote yes, if possible, and no, if not possible. And then he had the idea, if p minus 1 is not divisible by 4, it cannot be true. So he removed all prime numbers from his table. Where prime numbers p, where p minus 1 is not divisible by 4. Because of those where this is not divisible by 4, no chance. And then he made a very surprising observation. And we could do this if we would have time. We could do this and we would be very surprised. What's going on here? Very surprising observation. No prime number remained where it is possible. For all remaining prime numbers, they were small enough that he could try it by hand, but he was very experienced. So he got to go to rather big prime numbers. It was not possible to write them as a sum of two squares. Okay, I'm sure he said, yeah, okay, we are only up to numbers which are smaller than 10,000. This is for number theorists a small number. So he spent some other weeks and went up to 20,000. And still, he could not find a single example after excluding those where p minus 1 is divisible by 4, which he could write as a sum of two squares. And then he tried it again for perhaps a year, and he could not find. And then this is typical for Fermat, so making it for small, for larger and larger numbers, same result. Then he said to himself, this cannot be by chance, this must be true. And if he was convinced that something is true, although he had no proof, he called it a theorem. And so he wrote down theorem, Fermat, around 1650, a prime number, an odd prime number, because a prime number greater than 2 is P, is the sum of two squares if and only if, one direction we have proven, if and only if p minus 1 is divisible by 4. This is a shocking theorem. So there are prime numbers with billions of digits, where by hand you have no chance. By a simple computer test you have no chance. You need really to do it in an intelligent way. And the only thing you have to do is to subtract 1 and check whether it's divisible by 4. Then it's possible, and then not. So now a question, who finds this a cool theorem? Hands up. When I heard this for the first time, I found this so extremely cool. And a little remark, which makes it even more striking, to check whether a huge number is divisible by 4, you only have to look at the last two digits. And if the last two digits are divisible by 4, then this huge number is divisible by 4. So you have this number with billions of digits, and your grandmother asked you, is this perhaps divisible by 4? And you say, grandmother, take the last two digits. If this is divisible by 4, then it is, and otherwise not. And the reason is very simple, because we can write every number as a number which is divisible by 100 plus the last two digits. And since 100 is divisible by 4, it's enough to look at the last two digits. So it's a number is divisible by 4 if and only if, oh, this is perhaps not something you have seen, no, by 4, if and only if the last two digits are divisible by 4. So I was supposed to speak for 45 minutes, and there were 5 minutes to introduce me, so I have 5 minutes left. Last 5 minutes. And that's a little bit about the history. So Fermat had no proof. For him, it was clear that it is true, but no proof. And of course, we mathematicians want to see proofs. And actually, there are results where, and I myself have proven a very nice result, where for a long time you think the answer is this and this, and then an exception comes. So this is, of course, does not replace the proof. It took 100 years until a Swiss mathematician, where they have the good cheese and the good watches, Swiss mathematician, Leonhard Euler, fantastic mathematician, gave the first proof. Very complicated proof. And you could say, now it's over. There is a theorem, there's a proof, nobody will think about it. But we mathematicians, if we find the result super interesting, we wonder, is there a different proof? So important results, we look for different proofs. For important results, mathematicians want to see it differently. Look for different proof. So 50 years after Lagrange, the German mathematician Gauss gave a different proof. Lagrange, the French mathematician, a similar proof as Gauss, a German mathematician Dedekind, gave a different proof. So every 50 or 100 years, people came up with a different proof. And this list is not finished. About 30 years ago, my good friend, we were together PhD students, my close friend with whom I play music very often, it's named Don Zagier. And Google him on the internet. It's an impressive person. Gave a very short proof. This is called one sentence proof. You find it on the internet. Of course, it is one sentence for a top mathematician like Don. I even had to replace this one sentence by 10 sentences. And I could give this proof to you if you would give me a few hours. And then you would understand it. It's a very interesting proof. And if you have interest, perhaps you can ask your teacher to go with you through this proof. It is complicated for non-mathematicians, but it is a very, very nice, it's a trick proof. Yeah, you need to be a genius like Don Zagier to find this proof. And in American movies, there's always then a banner, and I show this banner, and this banner says, the end. Now I finish, and you can ask thousands of questions.
Well, okay, so let's thank Professor Kreck first.
Thank you.
Thank you.
Thank you.
Bye. Thank you.
Thank you.
Bye. Thank you.
Thank you.
So, right,
Thank
so
you.
I understand people have questions. So before we start, so first there were several questions we received earlier. The first question is, were you an OA student in high school?
By no means. I was well, in some areas I was okay. In most areas I was not okay. I found high school extremely boring. And guess which subject I found the most boring? The most boring subject I found mathematics. I found this so stupid because of I had to learn formulas without explanation and to apply these formulas without being taught what is behind the formulas. So I thought this is completely stupid. And so I even decided to make mistakes on purpose as protest. I protested against my maths teacher by, although I knew the correct answer in the tests, I wrote a wrong answer so that I got the worst degree. And my parents were very angry since then I could not pass to the next level. And so they forced me to go at least one step higher, and I did. So I was not good in mathematics. I liked very much ancient languages. I learned Latin and ancient Greek. That I found an intellectual challenge. If you try to translate Platon into German, then this is hard. There you need your brain. For mathematics, I didn't need my brain, but for Latin and Greek, I needed my brain. So I was not a very good student. Like Einstein.
Well, okay. So the next question, do you have any advices for middle high schoolers on number theory study?
So advices how, say again, how advices for? Say again, advices for what?
For number theory study.
So to study number theory. Yeah. I'm sure you find on the internet very many nice, simple number theoretical problems. So here's one nice problem in number theory, which you can then make more complicated. And I'm sure you know the question. Question, you add, 1 plus 2 plus 3 plus 4 plus 5 and so on, plus the last number is n. And what is the formula for this? Does somebody know the formula? Somebody knows the formula. N times n plus 1 over 2. Try to prove this. The proof is very simple, namely you add this and this, this and this, this and this, and you get always n plus 1. 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1, 3 plus n minus 3 is n plus 1. So you get always n plus 1, and how many summands do you have? You have n plus 1, n half. So n half times n plus 1. But now try it with 1 square plus 2 square plus n square, or 1 cubed plus 2 cubed plus n cubed, and so on. So you will find such problems on the internet and solutions. And if you have fun with such problems, you will get a feeling for some number theory. And so my advice is look for simple number. This is actually not simple. It's getting, if you write n to the k, it's very complicated. But at the beginning, it is simple. So look up elementary number theory problems and try to understand the proof and try to prove it yourself.
Okay. Next question. Can you talk about the links between math thinking and other activities?
So maths and the rest of the world. Is that the... yes. Oh, I'm very much convinced that if one has... So for me, mathematical thinking is the thinking in a consistent way. For mathematics, there is a central characteristic property, namely a statement is either true or the negation of the statement is true. And if you train your thinking to think consistently, also outside mathematics, I'm completely convinced that we would live in a different world. I'm completely convinced that we would have different politics. You know that there are politicians who one day say one statement and the next day the negation. You had even such a president. And this is not possible if you are trained like a mathematician. A true statement is true also the next day. So I think you, even in daily life, you will be different if you are trained to think consistently. And then, of course, if you would do medicine, or if you would be an engineer, or if you would be a craftsman, whatever, everywhere, this thinking is helpful. I repair many things myself. I try to repair things in my car, in my house, and I mainly use my consistent thinking. So I think it has a big influence.
All right. Then the next question, can you talk about your opinion on math competition?
Oh yes, I can tell you. I don't like it because of this. Of course. So of course I don't like it because I've never tried it. As I told you, I was not good in school in mathematics, so it was not a topic. But for me, it is very important to do mathematics slowly, not under time pressure. So if I do my research, it does not matter whether I think about a problem one day, 1 month, or 3 years, or 10 years. There are problems I'm thinking about, not every day, but come back to this for many years. And so under pressure, I would not be able to do something, and I don't think this is an important talent a mathematician must have to solve things quickly. And this is, of course, competition means you have to solve things quickly. But of course, there are outstanding mathematicians, for example, my friend Don Sagier, who would win any competition. He can do things so quickly. Or I have a young colleague in Bonn, perhaps you have heard the name Peter Scholze. He is considered one of the super mathematicians of this century. And he has won all these competitions without any problem. He is so quick, he solves them. So my answer is, if you have fun with competitions, take part and you will become better. But if you think you need to be good in such a competition to become a mathematician, by no means. I would be bad, and I became a successful mathematician.
Okay, thank you. So do people have any other questions? You can ask the question in the chat window. Okay, do you play Minecraft?
If you tell me what Minecraft is, I can tell you the answer. So probably the answer is no, unless it has a different name in German. I play the cello. You can listen to my playing on YouTube. If you type in my name, you will hear my music. I see somebody playing piano. We can play together. I am 74, but next week I will become 75. So I'm almost 75. Thank you. Yeah, I have a wife. I have a wife and I have 2 children. Thank you for happy birthday. And the best in my life is, of course, my wife and my children.
Bye.
Bye.
Do you play video games?
Yeah, no. Well, yes, I play sometimes this video game. I don't know what the name is, where stones come down, and if you fill a row, I think it's called Tetris. I like this very much. So if I'm tired of thinking about mathematics, then I play Tetris. But I hate shooting. So my grandson plays video games, and if I see this, I'm always shocked because of the pleasure seems to be to kill people. And I'm not a friend of this.
Okay, what's your highest score on Tetris?
Oh, I've forgotten. I've not played it for a long time. I was very good at some time, but I've forgotten.
When were you born?
I was born 1947. So directly after the war, and this was the poorest time in Germany. So we had only very, very simple food, and that's why I live so long, because of the simplest food is the most healthy. Everyday potatoes and vegetables, nothing more. And that's very healthy, I think. No hamburgers, this did not exist, although there is a city in Germany called Hamburg, but no hamburgers. No McDonald's.
Okay, I think students asked a lot of questions, and we really appreciate this very fun math seminar today. So let's thank Professor K again, and then hope everyone has a great summer. And the recording of this will be posted on YouTube, I think, shortly after the seminar, and we will also post the recording in the WeChat post as well. Great to see you guys, and hope to see you again in the next seminar.
Okay,
Bye-bye.
thank you.